So now we're going to use that factor theorem that we just learned, and now we're going to determine whether this polynomial has the following factors. So first what we're going to do is we're going to determine whether this is a factor of this. If this is a factor of this polynomial, meaning we can take it out as a greatest common factor and then you're left with something smaller. If it's a factor, when I divide it, it will have the remainder of 0. A shorter way to determine whether it has a remainder of 0 is just to find f of negative 1. So let's find f of negative 1 and determine what the remainder is. Negative 2 times negative 1 cubed minus negative 1 squared plus 4 times negative 1 plus 3. This becomes negative 2 times negative 1, which is positive 2, minus a positive 1, minus 4 plus 3, which equals 0. So the answer, is this a factor of the original polynomial? The answer would be yes, because the remainder is 0. The next question, let's do the same thing. To determine whether this is a factor of the polynomial up above, we're going to do the same thing. This time we're going to find f of positive 1. Remember, it's always the opposite of the sign. So let's find f of positive 1. Negative 2 times 1 cubed minus 1 squared plus 4 times 1 plus 3. So this is negative 2 minus 1 plus 4 plus 3, which is going to be 4. Since when I divide this factor into this polynomial, you get a remainder of 4, that means no, this is not going to be a factor of this polynomial. Because when you do the long division, you don't get a remainder of anything other than 0. A polynomial function cannot have more zeros than its degree. So in this example up here, the degree is 3. So the most possible zeros I might have is 3. Now I can have less. I could have 2 or 1 or sometimes none, but at most I can have 3. So once you find a 0, like right here, I have already found a potential 0 over here, there might be only up to 2 more. So once you find those other 2, you can stop searching. The last rule for this page is the Descartes Rule of Signs to determine whether the number of positive and the number of negative real zeros are of the polynomial function. If we can determine the signs, that might help us in determining where those zeros might be located. We can find the number of positive and negative real zeros without having to solve. The Descartes Rule of Signs theorem says, let f be a polynomial function that's in standard form, meaning descending order. The number of positive real zeros of f either equals the number of variations of sign, meaning from plus to minus. So this will be 1 variation, 2 variations, 3 variations, and so on. So the number of variations of the sign of the non-zero coefficients, or else equals that number less an even integer. The number of negative real zeros of f either equals the number of variations of the sign of f of negative x, or else equals that number less an even integer. So we're going to investigate the Descartes rule on the next page and dive a little deeper. For example, the following polynomial has two variations in the sign of the coefficients. Let's check that out. You'll see this is a negative coefficient, and a negative that goes to a positive is one variation in sign. It went from negative to positive. But then it stays positive to the next term, so that is not a variation. I have another variation, positive to negative, right here. Then it goes from negative to negative, which is not a variation. So that's how I know I have two variations in the sign of the coefficients. Since I have two variations, I'm also going to replace x with negative x. And let's see what that does. If I replace x with negative x, I have x. Negative x is going to be plugged into the original function. So I have negative 2 times negative x to the 5th power plus 7 times negative x to the 4th power plus 4 times negative x to the 3rd power minus 3 times negative x minus 5. Now let's rewrite all of this and get rid of the parentheses. This negative sign is going to stay because it's an odd power. So this negative times this negative makes it a positive 2x to the 5th. This negative will go away since it's to an even power. This negative will stay. This negative will also stay, but it combines with the negative 3 to become positive. So all I've done was rewrite this with all non-parentheses. Now let's look at the variations of this one. I go from positive to positive, which is no change. Positive to negative is one variation. Negative to positive is another variation. Positive to negative is another variation. So when I plug negative x into the function, I went from two variations now to 3. Okay? So this has 3 variations in sign. So to recap, f of x had 2 variations. F of negative x had 3 variations. That's going to help us in determining the number of zeros that we might possibly have. Because if you remember back to the previous page, if I pull this down just slightly, the Descartes rule stated that the number of positive real zeros of f either equals the number of variations of the sign, in this case was 2, so I might have up to 2 positive real zeros, or else equals that number less an even integer. So I could have either two variations or an even integer less that. So minus 2 would be 0. So either 2 or 0 zeros that are positive. For f of negative x, we plug that in to find the number of negative real zeros. So we either have 3 real zeros or that number less an even integer. So it'd be 3 or 1. Negative zeros. So we're going to go through some more examples here to dive in a little deeper just to make sure we can solidify this concept. For the following functions, let's state the maximum number of real zeros and find how many positive and negatives each zeros will have. So here we've got this function right here, and I know that the maximum number of real zeros is going to be 3 because it has to match the domain. How many sign variations does the f of x have? Positive to positive, positive to negative. There's one. This is one variation. But then it goes negative to negative. So there's only one sign variation. Since there's only one sign variation, we could expect to have either one positive real zero, or I could have 1 minus the next even integer, which would be 2. 1 minus 2, well, that makes negative, so that's not possible. So either one positive real zero or, well, there is no or. So I'm assuming it's going to have one positive real zero. Then the negative we're going to look at now. To do the negative zeros, the possibilities will be the number of sign variations when I plug negative x into the function. So if we plug negative x into the original function, we're going to get negative x cubed plus 2 times negative x squared minus 5 times negative x minus 6. So if I rewrite this, this is negative x to the third plus 2x squared plus 5x minus 6. You can see we have one sign variation here and another sign variation here. So I have two sign variations. So we're going to use this information to determine the number of negative zeros that are possible. We can either have two negative real zeros, or two less than that, which would be 0. So let's recall that I might have up to 3 real zeros. So if I have up to 3 real zeros, I could either have 1 positive and 2 negative, which would total 3, or I could have 1 positive and no negative, which means I only have 1 zero total. Let's try one more. Over here on the side, we're going to have another polynomial. This is to the 6th power, which means I could have up to 6 real zeros. The number of sign variations in the function goes from positive to negative, there's 1, and then negative to positive, there's 2. So my conclusion is I can either have 2 positive real zeros or 2 less than that, which is 0 positive real zeros. Now let's use this information to look at the negative zeros that are possible. We take negative x and plug it in and look at its sign variations. This becomes 3x to the 6th minus 2x squared plus 5x plus 4. So I have a sign variation here and another sign variation here, which is 2 sign changes. So I can either have 2 negative real zeros or 2 less than that, which is 0 negative real zeros. So to recap, I could have up to 6 real zeros. So to get that, I could have at most 2 positive and 2 negative, which is still not 6. So I clearly am not going to be able to get to 6. At most, I could have 2 positive and 2 negative, but I also could have 2 positive and no negative, which is only 2 zeros, or 0 positive and 2 negative, which is only 2 zeros, or 0 positive and 0 negative, which is no zeros at all. So I have lots of possibilities here. So now we're going to use this rational zeros theorem to list all of the potential rational zeros of this polynomial function. This rational zeros theorem states that if the function has a degree 1 or higher and is of this particular form, where each coefficient is an integer. Now, P and Q are going to be parts of the coefficients in this rational function, and if it's in lowest terms it's a rational 0 of f, then p must be a factor of a sub 0, which is the last term. Q must be a factor of a sub n, which is the first term. So we're going to use p, the numerator. P is going to be a factor of this last term. So p is going to be all factors of this constant, where q is going to be all factors of the first term. And we're going to use this p in this q to determine what the potential zeros might be. So in the next problem here, we're going to list all the potential zeros by finding p and q first. If we list all the integers p that are factors of the constant term is negative 12. All the integers q that are factors of the leading coefficient, which is 3. So let's start with p. P is the last term, or the constant. And I want to list all the factors that will multiply together to make negative 12. Clearly, 1 and 12 will be two factors that make negative 12. You can have a positive 1 and you could have a negative 12, but you could also have a negative 1 and a positive 12. So both options, both signs will be present there. You could also have 2 and 6. You could also have 3 and 4. All of those numbers are factors of negative 12. They're all potential divisors that create no remainder. Now I'm going to list all of the factors of q. Q are all of the factors of the first term, 3, where p was all of the factors of the last term, negative 12. So let's list all of the factors of 3. Well, the only two numbers that will make 3 are 1 and 3. The next step now is to divide. Find all possible ratios of what p divided by q are, and we have to go through all permutations of all of these numbers. So let's start with the first numbers. P divided by q, 1 divided by 1, so it'd be plus or minus 1. 2 divided by 1, 3 divided by 1, 4 divided by 1, 6 divided by 1, 12 divided by 1. Now we move on to the 3 for the denominator. 1 divided by 3, 2 divided by 3, 3 divided by 3 is 1, but I already have that. 4 divided by 3, 6 divided by 3 is 2, but I already have that. 12 divided by 3 is 4, but I already have that. So these are all the possible ratios of p divided by q. So all of these simplify down to 1, 2, 3, 4, 6, 12, 1/3, 2/3, and 4/3. If f has a rational 0, it will be found in this list. How many potential zeros are in this list? 1, 2, 3, 4, 5, 6, 7, 8, 9. But there's one of each sign, which means there's 18 possible zeros that I have to test all 18 of these zeros in this polynomial to determine whether it's a 0. That's a lot of checking. So let's try another one. This one I have a different polynomial. Here I've got 6x to the 4th minus x squared plus 2. So let's find p and q, and then p divided by q. And this will be all of the potential zeros of this polynomial. Remember, in order to find p is going to be all factors of the last term. So all potential factors that multiply together to make 2. Clearly, only 1 and 2 will be my options. Q are all factors of the first term. All numbers that make 6 will be 1, 2, 3, and 6. Now in the last one I'm going to divide p divided by 6. So here I'm going to divide p divided by q. So I'm going to get 1 divided by 1, 2 divided by 1, 1 divided by 2, 2 divided by 2, well that's 1, 1 divided by 3, 2 divided by 3, 1 divided by 6, 2 divided by 6, that's 1/3. So these are all the potential zeros of this polynomial. There are 1, 2, 3, 4, 5, 6 times 2, so there are 12 potential zeros. Now how do we narrow that down? Steps for finding real zeros of a polynomial function. We're going to use the degree of the polynomial to find the maximum number of real zeros. Then we'll use Descartes' Rule of Signs to find the possible number of possible zeros and negative zeros. Then, if the polynomial has integer coefficients, we'll use the Rational Zeros Theorem to identify those rational numbers, and use substitution or synthetic division, which I will introduce, or long division, to test each zero. So we're going to use these steps on the next couple pages to do some examples of how to find the zeros.